Thank you for coming, Kevin. And this is the 75th Bownocker Lecture Medal.
Wow,
So
thank you. Thank you very much, Mike. This is certainly an honor, and it's very nice to join all of those other names up there. I actually know Al Gore quite well. He calls me up every now and again. I'm one of his primary sources of science, and we actually took a trip to Antarctica together at one point in 2011. So what I'm going to talk to you about today is maybe a somewhat slightly different view of climate change, and with a special focus on how it affects the changes in extremes, which are so very important for society. And so that's what I hope to achieve today. And let's see. The first point, actually, I try to make is, and you know, we can go into this a lot in the question period, if you like, that climate change is certainly happening. There's general agreement among scientists that this is the case. If you look at any particular piece of evidence, any particular piece of data, you can find things that look to be at odds with the idea that the planet is warming, because there's all kinds of weather going on all the time. But when you put it all together, and in a physical framework, there's no doubt whatsoever that the climate is changing and that humans are primarily responsible. But what we do about this is something we might debate a little bit, and it involves worldview systems, value systems, and politics, unfortunately. So, why is the climate changing? What is causing the warming? Well, we are. And this is one of the pieces of evidence, the carbon dioxide record from Mauna Loa, from a friend of mine, Dave Keeling. Let me see if I can get the pointer to work here. Let's see. Try this button. No.
Yeah, that was it. Try that again. It was over here.
Why doesn't this work? There we go. And so there's a sawtooth character to this, which is the planet breathing in and out as it undergoes photosynthesis in the northern hemisphere. There's a drawdown of carbon dioxide in the spring and in the summertime, and then it increases as there's a decay of leaves and so on the forest floor. But that annual cycle is huge, but it's dwarfed. It's dwarfed by the overall trend that you can see here. And I want to point out some things about this trend. The trend is increasing over time, in spite of efforts such as you may have heard of the Kyoto Protocol, which was designed to bend this down in the other direction. And in spite of things like the Paris Agreement, again, that has that goal, instead, the rates of increase in the last few years have been the highest on record. So here's what happens to the global mean surface temperature. This is the one from NOAA. It's estimated back to about 1875 in this case, something like that. As you go further back in time, it becomes a bit more ragged back in here. There's no data in Antarctica prior to about 1958, the International Geophysical Year. And so the record is a bit less complete back here. Some of the raggedness stems from that incompleteness, but there is raggedness nonetheless in more recent times. And so the warmest year on record is 2016. 2017 is here. 2015 is the second warmest in this particular record, and the pre-industrial value is estimated on here. So this is before about, before about 1870 or thereabouts even. This is the estimate as to what the value is. And so right now we're more than 1 degree Celsius above that particular value. So here's the annual values of carbon dioxide prior to 1958. This is estimated from bubbles of air and ice cores in Antarctica and Greenland. And And the scale is on the right-hand side, going from 280 parts per million by volume at pre-industrial levels to over 400 now. I plotted these together to suggest that there's a relationship between them because we can prove at NCAR that that's actually the case. But it requires a model that relates the carbon dioxide to the changes in the climate, the changes in temperature. So we'll say more about that kind of thing coming up. Half of the increase in carbon dioxide has occurred since 1985. Since 1985. It's relatively recent. This should be alarming to you, and all of you in this room, I would guess, have participated in this in one way or another. So what I do in a lot of my research is to focus on trying to track the energy as it flows through the climate system. And so the overall suggestion from the climate change aspect is that the climate is changing from the increases, primarily from the increases in greenhouse gases, carbon dioxide in particular, in the atmosphere. And we expect, therefore, that it acts as a blanket. It traps some of the radiation. It prevents some of the radiation from escaping to space. And so the planet warms until the outgoing radiation can increase to balance the incoming radiation which is trapped in the system. And the outgoing radiation is very much temperature dependent, and so this causes a warming. But there's many feedbacks and complexities, which we'll talk a little bit about here today. That I would argue that one of the most fundamental measures that the climate is changing is the energy imbalance. Earth's energy imbalance. We sometimes refer to it as EEI, the Earth's energy imbalance. So here's a schematic view of, two-dimensional view of the overall global energy imbalance. And I've only put numbers on the top three values here. The incoming radiation, the reflected amount, the difference between these is about 240 watts per square meter. Never mind if you don't understand the watts per square meter. I'll say more about that in a minute. Remember the 240. And there's about 239 going out. And so there is a net imbalance of about 1 watt per square meter. Now, one of the key things about this is that the Earth's energy imbalance is the net effect after all of the complicated stuff in the atmosphere has gone on, from clouds and pollution, aerosols, and from water vapor feedback, and for those of you who know what that is, and so on. And so this cuts through a lot of the uncertainties that other people are dealing with in terms of just what's going on at the top and within the atmosphere by itself. And so let's put this in some kind of context. So round it off. Instead of 0.9, 1 watt per square meter, it's very close to that, and it may well be that now. And it varies a little bit over time. For comparison, a Christmas tree light, standard Christmas tree light's about 0.4 watts. And so this is about 2.5 Christmas tree lights for every square meter. 1 square meter is about 10 square feet. If you add this up over the area of the Earth, this amounts to 500 terawatts. 12 zeros after the 500. And you can compare that with all of the U.S. electricity generation in 2017, which was 0.46 terawatts. And globally, you add it all up globally, it's of order 1 terawatt. And so this is a factor of 500 larger than all of the energy that's generated around the world. That makes this number large and of considerable consequence. But it also says that the direct effects of humans in affecting the climate by space heating and other things is relatively small. The direct effects are small. Locally in cities, the number can get up to, say, 30 or 40 watts per square meter, but it's relatively local. And so it's mainly through the interference with the natural flows of energy through the climate system by this greenhouse effect, by this layer of gases that absorbs the outgoing radiation that matters. So that's one perspective. It's very large compared with the human component that is direct. But then the one imbalance the 1 watt per square meter imbalance is very small compared with the overall flow of energy through the climate system, which I pointed out is about 240 watts per square meter. 240 coming in, 239 going out. And so on a day-to-day basis, you don't notice this. It's not how we experience climate change. So what we have to look for then to compete with the natural flow from the sun is where does it accumulate? And it does accumulate because it's always in the same direction, it's the same sign over the entire globe. So if there's more heat, where does it go? Where does it accumulate? Well, it warms the land and the atmosphere. It goes into the ocean. There's heat storage in the ocean, which expands, and that raises sea level. It melts land ice, which raises sea level, puts more water into the ocean. And it melts sea ice. And then you have to warm the melted water to the ambient temperature. And also, the big complication, it evaporates moisture, which changes rainstorms. Whoops, 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 whoops. Go back. And cloud, and this can change the amount that's reflected to space. And we've done quite a bit of work on this kind of thing. And, on a day-to-day basis, the weather systems don't know about this constraint, about the overall energy balance that it has to balance. And so it can very easily happen on a weekly basis or even a monthly basis. There's a whole lot of cloud and a great big storm, and it blocks more of the sun. And so there's an energy imbalance, but it's pretty amazing that over about 5 months, all of that tends to even out. And if you get a sunny period, it's compensated for by a cloudy period a month later or something like that, or maybe in a different location. So it doesn't have to be in exactly the same place. So a lot of this averages out, it turns out, and there's a lot of work that's been done on that. Now an example, humans, what happens if you heat your bodies, right? Well, we sweat, perspire, and it's the evaporation of moisture from the skin that keeps the body cool. And this can work quite well in dry climates. In Colorado, where I'm from, or out west in general, we can use evaporative coolers instead of air conditioners. They call it swamp coolers also, to cool the air at the expense of moistening it somewhat. And this works quite well for the planet Earth because 70% of the planet is water. And so the heat goes into evaporating water instead of raising temperature. And of course, this is one of the key things which drives the water cycle, the hydrological cycle. So this depends on whether or not water is available for that to happen. Another example, if the sun comes out after showers, the first thing that happens is that the puddles dry out before the temperatures increase. It's a little oversimplified, but it's largely true. Some examples, one example of places where the energy accumulates is in melting of ice, as I mentioned before. So glaciers are retreating in general around the world, and Greenland is melting in particular, and a piece of Antarctica is melting. And Arctic sea ice is going down. This year the value is probably slightly above this line, but still consistent with an overall downward trend. What about land? If the land is wet, the heat goes into evaporation. So it doesn't accumulate in that case. In a drought, this is when the heat can accumulate. And it does so by firstly drying and then secondly heating the land. And so how large is this effect? 1 watt per square meter over a month. If you accumulate that, there's 720 hours in a 30-day month. And so it's equivalent to 720 watts per meter squared for 1 hour. And 720 watts is the power of a small microwave oven. And if we say 1 square meter is about 10 square feet, this is equivalent, this energy imbalance is equivalent to 1 microwave oven at full power for every square foot for 6 minutes. You can boil water in what, 2 minutes in one of these ovens? If you put paper in it, maybe you could try this. Experiment for you. You put paper in here, turn it on for 6 minutes, see what happens to the paper. I bet it catches on fire. No wonder things catch on fire. And so this has been especially relevant for what's happened out in the west. So what about the oceans? I suggested that 90% of the energy imbalance actually ends up in the ocean, changes the ocean heat content, OHC. There are new observations in the ocean. This is the distribution of these Argo floats, as they're called, some 3,881 in February of this year. And they go down, they reside about 1 kilometer below the surface. They go down to 2 kilometers, and then they pop up to the surface and make measurements of temperature and salinity, and then they radio that information back to ground-based stations. And we are getting reports all around the world now from these Argo floats about once every 10 days or so. And so we have good observations now, and that has enabled us to make better use of the old observations, and so we can actually do pretty good reconstructions of the ocean heat content back to the IGY, back to the 1958 or thereabouts. And this is what I believe is the best reconstruction to date. And by subsampling when at a recent time when we know what the answer is, with the number of observations we had in the more distant past, we can actually estimate how well we're doing, and that's the basis of this error bar back in here. And you can see in the oceans, there's not that much warming until after about 1985. There was a big volcano went off in here that helped to cause this cooling. And since then, the warming has been very steady and upwards. There's some small dips in here. I said before, 2016 is the warmest year on record. It's not here. 2015 was higher, and 2017 is high. 2017 is the warmest calendar year on record for the oceans as a whole, and therefore for the planet as a whole. 2015-16 was this big El Nino event. And actually, this is the signature of an El Nino event. The heat came out of the ocean, and that contributed to why 2016 is the warmest year on record, because there's, if you like, a natural variability component to the global warming that takes some of the heat out of the ocean, puts it into the atmosphere, mainly through evaporation out of the oceans, evaporative cooling of the oceans, moistening the atmosphere, invigorating storms, and having consequences there for the weather around the world, but cooling off in terms of the overall ocean heat content. This is the distribution of the ocean heat content in the vertical. So this is depth over here. This is 60 south. Antarctica is over here. This goes to 70 degrees north. And you can see a lot of penetration into the deep southern oceans and in the southern hemisphere. And also, to some extent, in the northern hemisphere. This is nearly all going into the Atlantic and not into the Pacific, and there's some spots that have actually cooled, and it relates in part to ocean circulation as to how this ends up the way it is. And then this is an update from my colleague Li Jing Chen. He just spent a month with me at UCAR, and they update this every quarter. And so the latest one is April through June of 2018, and this is the value here. So this is the warmest quarter on record. Warmest value on record for any season going back as far as we can go. And this is the pattern of the integrated. This goes down to 2,000 meters, and it's relative to the average from 1981 to 2010 of the ocean heat content. You look at this for a few minutes, and you can see, well, there's a few spots that are below normal, but generally it's in the oranges and reds. And one of the warmest spots on record is where something happened very recently, and there are reasons why it happened in that particular spot. It's one of the places where the ocean heat content is the warmest in the world. A consequence of the glacier melt plus the ocean heating is that sea level is rising. So these are completely independent measurements from altimetry in space, looking at the sea level record. And overall, since late 1992, when the record starts, the overall rise in sea level, global sea level, is about 3 inches. It's not distributed uniformly. It's distributed largely with the same pattern as the ocean heat content. There are some dips and peaks in here. There's a peak in here related to El Nino because more rain occurs over the ocean. in El Nino, less over land. That's why we have droughts and wildfires over land. And this was a period of La Nina, where there was a tremendous amount of rain. Actually, there was quite a bit in the Mississippi and also in Siberia. But the key thing here was a tremendous amount of rain in Australia. And Australia doesn't have a riverine system, and so it forms a big lake called Lake Eyre. And Australia filled up with water, and it takes about 18 months for that water to evaporate because it doesn't run off in rivers back into the ocean, but eventually it ends up back in the ocean. And so this is extra water on land, not in the ocean. That's what's the cause of that big dip here. And so this also is a very clear signature that the planet is warming. So one of the things we can do as scientists with our climate models is, I put on the top here, you can have fun. You can play God. You can change things. You say, all right, let's take our climate model and run this climate model. Here's the observed record in black here. And we can take our climate model, and in this case, there's a whole bunch of climate models under these international projects. CMIP 3 is the old one, and CMIP 5 is more recent. Of all of the models, in any individual year, there's a lot of weather and fluctuations. It's only when you put them all together, you end up in the most recent case with this red curve here, showing how well it agrees with the overall observed temperature record. You can see that there are some dips, which turn out to correspond to big volcanic events, natural forcing events. There's some here, which are probably overdone a little bit by the models. The El Nino events are not synchronized between the models and the real world, and so the fluctuations from El Nino events are not, don't agree with what has happened in the individual record. But what we can do then is to take out the increases in carbon dioxide and other greenhouse gases and the air pollution and rerun these models, and we get this result here. So here you can now clearly see these three volcanoes, Mount Pinatubo, El Chichon, and Mount Agon, and this is what the climate model suggests would have happened to the global mean temperature in the absence of the increases in carbon dioxide and so on. And this is the observed record. And so you can see the difference here is this big bite after about 1970 or thereabouts. This is when global warming has really kicked in, and the signal of global warming, if you like, is outside of the noise of natural variability. And you can see the magnitude of the warming that has occurred. So what are the expectations when we deal with extremes, and in particular, climate events? That's what I want to spend the rest of the time on, if we can. And so one of the mantras that has been used by climate scientists for a long time is that we can't attribute a single event to climate change. These are chance events. And all we can say is some average statistical statement. But we think this is no longer the case, and it depends how you frame the question. And the key things I would point out is that changes in the atmospheric circulation with climate change are small. We can show this in our climate models. We can run them for 100 years. And the changes in the atmospheric circulation from climate change are very small. You can only identify it with a very large number of runs to average out all of the noise of the weather, if you like. And in any case, every weather system is different than all the ones that have gone before. There's infinite variety that occurs in the atmosphere. And so the individual character always outweighs the climate signal. And so there's been a lot of studies that have aimed to attribute what has gone on with a particular weather event to natural variability or to human-induced climate change. And they find, natural variability dominates, the weather dominates. It's simply a statement of this. And so they should find that, but it's not the correct framing. Instead, what we have suggested is that you should take an approach that takes the phenomenon as given. The storm occurred. And let's ask the question instead, how did the outcome from this storm and the impacts of the storm change because of the environment in which the storm is now embedded? The fact is that the environment is warmer and it's moister than it used to be in general. And so this is a summary of this, that we have dynamics versus thermodynamics. So this deals with the temperature and related. This deals with the motion and the phenomena. So it deals with phenomena, movement, development. It's chaotic, it's unpredictable, and every storm is unique. But the environment is warming and it's getting moisture. Sea level is going up, and this is robust and it's predictable. And so this has implications for the environment in which all storms occur. And in general, it's warmer by over a degree Fahrenheit. It's moist, depending on where you are. This is relative to about 1975 or thereabouts. Overall, it's, as I said before, it's more like 1 degree Celsius. And it's moister by 5 to 20%. This is mainly where there's water over the oceans. The ocean heat content is much higher. This is a memory of the system. And sea level is much higher by, at least 8 inches, maybe 9. So these are the memory. And so on the right-hand side here, this is actually the water vapor record going back to 1979. This is the sea level record you saw already. So what about the atmosphere? So in the atmosphere is generally warmer, and the air can hold more moisture. This is a law called the Clausius-Clapeyron equation. You can look it up or Google it or something like that. And it turns out, in general conditions at the surface, it's about 7% per degree Celsius, which is about 4% per degree Fahrenheit increase in temperature. So if there's a 1 degree Celsius increase in temperature, you can expect with constant relative humidity, there's about 7% more moisture in the atmosphere. And this is about what we observe. And so with global warming, there's more heat, more trapping of the heat in the system. There's more drying, there's more evaporation, and there's more moisture in the atmosphere. And the consequences of this is that where it rains harder. And in places where it's not raining, the increased drying, the more evaporation, means that the drought. It doesn't cause the drought, but the drought sets in quicker and things dry out faster. And so this is my attempt to illustrate this, that we have a parcel there, and it has some moisture in it, and something kicks it off to cause it to rise. It could be an advancing cold front, or it could be going up against a mountain or something like that. And so it expands and it cools as it expands, and it rains like hell. Look at that. And so we have, in this case, I've illustrated it with a thunderstorm. Most precipitation comes from moisture convergence. It doesn't come, I don't know whether you thought about this, or I don't know whether this is taught in classes. Why does it rain? Where does the moisture come from? Well, it doesn't come from evaporation underneath the storm. That's relatively small. It's only a few percent of the actual rain, if there's any substantial amounts of rain. And instead, oops, where did it go? There we go. Instead, the moisture that causes the rain comes from quite some distance away, and the storm reaches out, grabs that moisture, brings it into the storm, and so if there's more moisture in the environment, there's more rain. And so if you're out in the summer on a golf course, there's some gusty winds, and you say, oh, clear sky, why is it windy all of a sudden? And then you look over in the distance and you can see, oh, a couple of miles away, there's some thunderstorms brewing. And this is the thunderstorm reaching out. One way of thinking about this is the circulation associated with the thunderstorm. It's reaching out, grabbing the moisture, bringing it into the storm, and so if there's more moisture in the environment, it rains harder. And so this is the actual record for the 48 contiguous states, the U.S. This is the temperature at the top here, and this is the precipitation. And so this is 1900 going up to 2016, and the star is 2017 on here. You can see that there's an overall upward trend, quite distinctive. There was quite a warm period back in here, around about the 1930s, called the Dust Bowl era. And then down below I've got the precipitation. So I want to point out a few things here. The first one is back in the 1930s, the Dust Bowl era. This was a period when there was a whole bunch of droughts, very intense droughts, and each one of these droughts corresponds to a peak in the temperatures. This applies especially in the summer half of the year, less so on the annual average, but it does show up in the annual averages. And you can see a number of very strong droughts in earlier years during the century, during the last century. I would characterize the precipitation as something more like this. There was really no change up until about the 1970s, and it's somewhere in here, depends on which season you look at, as to where you would put this break point. But since then, there's been about 7% more rainfall over the 48 contiguous states, and all of this has occurred east of the Rockies. So it includes this area. But you can see the variability in precipitation is much larger. So the overall trend is not as significant at all. But if we went back to this climate here, places in Ohio and other places would really be hurting for the amount of water that's available. And yet we're not quite sure how much of this is due to climate change and how much of this is due to something else, which we can talk about if you like later. And then if we look at the warmest year on record for the 48 contiguous states, it's still 2012. 2017 is not far behind. And there was a major drought. This drought cost $75 billion, thereabouts. And yet, for the annual mean, it's still relatively small compared with ones that occurred back in the 1930s and last century. The hot and dry conditions tend to go together. This is the actual pattern that was published by the National Assessment that was published last year. This is 1981 to 2015, a relatively long period, compared with the first 60 years of the 20th century, a little bit shorter for Alaska, as to where the warming has occurred. And it's occurred most strongly in the west. Remember what I said. The main increase in precipitation is east of the Rockies. Well, that's somewhere here. And the biggest warming is in the places where the precipitation hasn't increased. And in the east, and in particularly in the southeast, it hasn't actually warmed at all. Or one way of thinking about it is this period was relatively warm in the southeast. But also, this is an area which has gotten quite a bit wetter. And so the extra moisture keeps the temperature down. On the other hand, when we look at precipitation events, east of the Rockies in particular, it's gotten a lot more extreme. When it rains harder. And so the extremes of rainfall are increasing as a consequence of the extra moisture in the atmosphere. So here's a summary as we go into some of the examples. With a warming climate, we have more high temperatures and heat waves, wildfires and other consequences, and fewer cold extremes. And there are more extremes for the hydrological cycle. Both of these things, not at the same time, of course, not at the same place, but, and this is what causes a lot of confusion to the general public and with policymakers. But there's increased risk of both flooding and drought with climate change as a result of these changes. It also gives rise to more intense storms, hurricanes, and tornadoes, and it's a major challenge for water managers. So I want to do some quick examples. I haven't got time to go into these, so I'm going to skip through these very quickly. This is back in 2015. I said 2015 is the start of the El Nino. Some of the patterns as to where these occur are related to El Nino. And so Australia, look at this. One place, minimum temperature, minimum 93.6 degrees Fahrenheit. Unbearable. And 87 wildfires in New South Wales at that time. Wildfires all over the place. You may have seen a lot of publicity related to this big wildfire at Fort McMurray in Canada. There are also floods all around the world in different places. Extensive flooding in South Carolina and Louisiana in particular, not that far from here. And there are also some heavy rains in California that led to the demise of this particular tree. It fell down. Oh. And then 2015 is the year when there's most active tropical storms, hurricanes, typhoons, And these are some of the examples, including Hurricane Matthew in the Carolinas in October of 2016. You know, there were 3 storms lined up. Here's Hawaii, threatened Hawaii in 2015. You know, and this year we've had 2 that actually hit Hawaii. And the strongest storm ever in the southern hemisphere, Winston, went through Fiji. This is early 2016, still part of the El Nino conditions. And then in early 2017, there was a coastal El Nino. I need to show you, this mudslide was incredible here. Look at this mudslide, see if it shows up here. So look at this. There's a woman in here. Look at that. She emerged out of all of this, somehow came out of this thing. There she is. You have to wait till she actually makes it. She actually makes it and gets out of there. Incredible. Sort of things that were going on not that far away, not that long ago. And then, you know, this past last year, there were wildfires galore in various places. One of the most spectacular was in Santa Rosa. This is a before and after. There were 50 dead and 6,700 homes that burned in that particular event. And there were more wildfires down in southern part of California, even in December, late in the year. And, you know, it's not just in the U.S. There was also major wildfires in parts of Europe, in particular, on a couple of different occasions in Portugal last year. More than 1,000 died in heat waves. In floods in the monsoon of the summer of 2017 in Nepal and India and in Bangladesh. And then we had these hurricanes. And so I wanted to dwell just a little bit on a study that we did relating to these particular hurricanes. And we asked the question, you know, were these disasters natural? And, well, hurricanes are natural. But no, they were supersized or supercharged because of climate change. And I suggest that these events would not have occurred without the human-induced climate change. So, and in addition, they were very poorly prepared for. I want to say a couple of words about both of those things. So here's the overall picture with regard to hurricanes. This is the distribution of them. Most of them occur in the Pacific Northwest, where they're called typhoons. It's only about 10% of them occur in the Atlantic overall. And with climate change, we expect more intense hurricanes, bigger hurricanes, longer lasting hurricanes, and more flooding rains. In 2017, there were 17 named storms, normal is 12. There were 10 hurricanes, normal is 6. And there were 6 major hurricanes above category 3. So this is some of the outcome from Harvey. I have a whole host of slides related to this, but I just want to show you a couple of things. So I mentioned before the Argo floats. This is the distribution of Argo floats in the Gulf and in the Caribbean in August of 2017. And so this is the track of Harvey, and it lingered around here in the Houston area late in the month. And these are some actual profiles of temperature from a number of buoys that were floats that were in this area here. And this is sort of before the temperature was over 30 degrees Celsius, over 80 degrees, 86 degrees Fahrenheit, 87 nearly, and after. And so it cooled off the top of the ocean. It mixed some of the heat down because of the strong winds, but it's mainly the effects are above about 80 meters or thereabouts. And so we're able to measure that, and we can do this and map it for the entire region. It turns out in the Gulf that the ocean heat content was the highest on record prior to Harvey. And this is the actual pattern of relative to 1961 to 90. This is the base period, and this is what the anomalies look like. This is where a tremendous amount of heat was residing at that time. And then this is after, from the 1st to 20th of September. And then this is the difference. And so this is the effect of Harvey. When these storms occur, they churn up the water, they mix it down, they cause tremendous amounts of evaporation into the atmosphere. That provides moisture that fuels the rains, the heavy rains, that in turn release the heat that went into evaporating the moisture in the first place, and that's the fuel for the storm, and we can measure that. And so we can measure the loss of heat in the Gulf of Mexico in this box here, and it turns out to be 6 to 7 times 10 to the 20 joules, a huge amount of heat that came out of the ocean and cooled it off. And that's one of the reasons why we don't have a lot of activity this year, because the Gulf has cooled off from all of the storms that occurred last year, including Irma. And there's a little bit of a sign of Irma in here, which is why we only use this particular box. And then Maria was a little bit later. This is the rainfall associated with Harvey. And so you can see it propagating up and then slowing down and parking over Houston with over 60 inches of rain in a number of places that were recorded. And so this is the overall total that we were able to compute based upon the best products that are available. We have a time series for this. And we computed that the amount of latent heat that was released in the rainfall was 6 times 10 to the 20 joules. Didn't we see that number before? Where was it? There it was. 6 times 10 to the 20 joules. And so this is the first time anyone has been able to match the rainfall and the amount of rain to the sources of the moisture, the evaporation from the ocean, through completely independent measurements. And I would argue then that if the ocean heat content had been less, the rainfall would have been less. So how well were people prepared for Harvey? Well, this is an example of a flood that occurred in the Houston area in April of 2016. And they had another flood that was a so-called 500-year flood in 2015. Major flooding is not uncommon in Houston. 60 inches of rain is, but only 1 in 6 had flood insurance. That's incredible. When Hurricane Ike went through the area in Galveston and Houston, and it claimed 113 lives in 2008, there were proposals for a number of large-scale flood control projects and drainage systems to be built in and around Houston. And the people of Houston voted it down. And that's happened 3 times. There's unbridled growth in Houston. There's no zoning codes. There's no decent drainage systems. There's no protection. There are 2 major what used to be reservoirs where people have built. These are areas where I reckon they flood about every 10 years or less, maybe less. You know, we talk about 100-year floods and 500-year floods and 1,000-year floods. These are 10-year floods in Houston. And so they haven't done anything about this. And one way of interpreting this is that they voted to suffer the consequences. And this is what we're doing in the United States with regard to climate change. I don't have time to dwell on Irma, but there was tremendous damage in the islands. And also, in Puerto Rico, I have a number of slides related to that, and of course there's a tremendous number of deaths there, and they're still suffering from the damage that occurred a year ago in Puerto Rico. And then earlier this year in Japan, in July, there was some major flooding in the southern part of Honshu, and a tremendous amount of damage that occurred, over 7,000 homeless. And then later in the month, the same month, this is the map of the actual distribution of temperatures over 30 degrees Celsius, which is 86 degrees Fahrenheit. And in Tokyo, they actually had temperatures over 40 degrees Celsius. Never been seen before. Also South Korea, which is just over here, was suffering in much the same way. And then in 2018, we've had major fires again in California. In this case, different fires actually merged together and became what was called the Mendocino fire. It's the biggest on record. And again, tremendous damage and costs. And Here's a spectacular picture I couldn't resist putting in of a so-called pyrocumulus, where the fire actually creates its own weather. And this was a summary that was put together by the Washington Post of some of the other events around the world in different places, of some of the extremes that have occurred this past summer, in association with, remember, the warmest ocean on record, and one which is getting warmer still. Southern India, southwest India, down in this spot here, Kerala, experienced major flooding, the worst flooding ever since the 1920s at least, and over 370 people died in that region. And then subsequently, after that, they've actually gone into drought. So this is the amount of rain that actually occurred down there, over 300 millimeters. Then we have Mangkhut that went through the northern part of the Philippines not very long ago. Over 81 dead. A lot of mudslides occurred in that region, and over 66 were killed in Hong Kong, and it went from there into China. And then we have Florence, of course, that occurred from 13th to the 16th, and there's, over 33 people dead, and let's see, you can see a number of different days here, so you can actually watch Florence. Whoops. Go back. Where are we here? Try again. I want to try and point, all right? It disrupts things. So there's Florence over there, and you can see a number of day-night sequences as it makes landfall in the Carolinas, and North Carolina in particular. Whoops, it's doing it again. Let's try it again. And so this is the outcome. A number of areas where there were more than 20 inches of rain, total precipitation in centimeters. So this is 300 millimeters, 400 millimeters. And here, and this is the what they've done in NOAA is to estimate that all of the purple areas in here, it was more than 1 in a 1,000-year event, in spite of the fact that I can show you another map, if you like, of Matthew that occurred 2 years ago that had a swath all the way up the Carolinas that was over a 1 in a 1,000-year event also. And yet it's reported that only about 1 in 10 had flood insurance, which is incredible. And of course the consequences of that are that you and I end up paying for their lack of flood insurance through FEMA. And so that's all I'm going to do in terms of examples. We cannot say that these events were caused by global warming. That's a poorly posed question. But it's highly likely they would not have occurred the way they did without global warming. The impacts in particular are enhanced because of the heavy rains or the extra drying. And so climate change is happening. It's caused by human activities. For many events, we can estimate that the difference from climate change in terms of the water vapor in the atmosphere is in this 5 to 20% neighborhood. And this means that records are broken and thresholds are crossed, and things break, or they flood, or they burn. And there's extreme nonlinearity to this. And so instead of $1 billion in damage, you end up with $100 billion in damage because you cross thresholds and things break. And the trouble is that this nonlinearity is not taken into account by economists. And so the economists greatly underestimate the true damage that is occurring. So, Harvey was 120, some as much as $180 billion. Maria was over $100 billion. Irma was $60 to $80 billion. It's very easy to see that with $1 billion invested wisely, you could have prevented most of this damage. So climate change is happening. It's caused by human activities. It already costs at least tens of billions of dollars per year in damages. We can either mitigate it, stop or reduce the emissions. We can adapt to it, which means planning for the consequences and build resiliency. Or we can do nothing and suffer the consequences. And that's the policy of the US government at the current time. So I want to end the last two slides on a more optimistic note that, we really could do something about this on a fairly rapid time frame if we set our mind to it and go about it in the right way. And you can ask me what that right way is, but I think it involves a carbon tax, putting a price on carbon. And so here's some examples in the past. This is New York City in 1900, and there were all of these horse and buggies. And then this is New York City in 1913. 13 years later, I think somewhere down in here there's a horse and buggy, but it's nearly all automobiles. And it happened in 13 years or less. And this has happened actually in the past, that once the US has set their mind to it, you can, prior to the 1870s there were sewers in individual houses, but they weren't collective. One house was not coordinated with the next house, and towns were not coordinated. And as a result, there was an awful, stinking mess prior to about that time. And then when you start building town sewer systems, suddenly everyone recognized the value. Subway systems were initiated and built very rapidly. The national grid was established in 1938. The interstate highways, some of you young people may not realize, they were only established in 1958 on, but once they got going, then they became nationwide and they were utilized a great deal. And I've just put this in to indicate the role of satellites on everything. Really took off maybe about 1969. And some of you will have experienced some of these revolutions that have occurred. The internet really developed since the 1980s, and cell phones have only been around since the 2000s. No resistance to these things, they've been embraced. But what we need is the next energy system. Smart grids and transmission and storage are key issues. And so this is, I think, almost the last slide. So, wind power. Why don't we have one of these on top of every single building? It'd be wonderful. And then there's hydropower. We have solar power and storage systems. This is in here to indicate storage systems. And then this is indicating transmission. So transmission of power from the places where you can generate it to the places where you need it. And so this is one of the problems with solar, of course, is that there's no solar at night. And wind power can also be intermittent. This is a very valuable way to store power. And so if you can couple this with these others, you can generate more continuous power. But transmission is becoming cheaper, and there are new ways of doing this using direct current instead of alternating current. And there's a revolution waiting to happen. And the US could lead this, but at the moment that's not the case. And a lot of this could happen on a time frame of 10 to 20 years. So there's some optimism that we could make real changes if we embrace this kind of thing. But without it, whoops, there's one slide missing. Hang on. No, I'll show it tomorrow. So without it, we're in deep doo-doo. So I'll stop there. Thank you.